Jones from Optimism.
What's up, y'all? Okay, so I know we've had a lull. We're coming up on a long day of talks. So here's my strategy to get y'all's attention. I requested a song to kick us off, and the winning request was Celine Dion. So I will play one quick melody, and then you will all start clapping so loudly, and then everyone will just come in from that. Okay? Sound good? All right. Thank you all for bearing with an incredible jam-packed long day. And I am Ben, and I'm here to talk to you about Optimism's next-gen fault proofs. So I'll start us off with some cool images of our, wrong slide. There we go. Okay, look at this. This is a cannon. It's not. Oh, I skipped my countdown. I got like 30 extra seconds here, y'all. We're gonna have so much time for questions. All right, look at this. That is a cool, sexy, sci-fi Optimism cannon. Look at that. That is a cool, sexy, sci-fi Optimism cannon. And that is what I am here to tell you about today, cool, sci-fi Optimism cannons. Does that sound good? Yeah. Okay, not really. I will first start by telling you what is cannon, and then we'll talk a little bit about it. Okay, so cannon is a lot of things, and I probably won't even be able to cover all of them right now, because I do want to hopefully have some time for questions. But one thing that cannon is the multi-step fault proof that we've built for Optimism Bedrock. Another thing that it is the ability to run arbitrary Golang in a rollup. Very exciting. Perhaps the most important thing that it is EVM equivalent. That means that it follows the rules of the EVM down to the letter. It means that your L2 systems running on Optimism will follow exactly what you expect from L1 down to the letter. How cool is that? Oh, yeah. Okay, what is Bedrock Edition, you might ask? So Bedrock, Optimism Bedrock is our next-gen release that is coming up for Optimism. Basically, we've taken all of our learnings building these protocols over the past 2 years and condensed them down into one beautiful, minimal code base that will be the basis for all of the building over the next few years from Optimism. It is built to last. That's why we call it Bedrock. Oh, yeah. Okay. What is the principle that we followed in building Bedrock? There's basically two, and really I guess I should have put one if I were to follow the principle, because it's all the same thing. Reduce, reuse, recycle, minimize, minimize, minimize. What have we learned over the past 2 years of building these protocols? It's that security is very important. And where does security come from? It comes from a lack of code. Because the more code that you have, the more risk you have of introducing bugs. So the name of the game for everything that we're building with Bedrock is do it right and do it small. Not a slogan you'll hear all the time from folks like me. Okay, so how do we apply that in the case of cannon, which is the fault-proof part of Bedrock? Well, the first thing that we do is we reuse Geth. We are not rolling our own system. We must reuse what Ethereum has built and developed and expanded for years and years and years. And so that's what's called mini-Geth. Another thing that we do is we use a very, very, very minimal instruction set, in fact, a reduced instruction set computer, a RISC, that we run all of the code base on top of. And the last thing that we've worked very hard to do is work it down to the fundamental abstractions that make up these rollup systems. And that's important because what we've learned over the years is there's actually a lot of ways to build a rollup that works, but it doesn't quite sit right. It's not quite what we're looking for. And so with Cannon, we've finally got the pieces right. We've put them all in place. Very exciting. There's a GitHub. Okay, so very quickly, the L2B guys asked me to go deep on this. So I'm going to assume that you have a little bit of background on the multi-step fraud proofs and how this stuff should all work. But if you don't, here's the one-page refresher. It's like a sandwich. Shout out to Dan for the OG sandwich analogy, but I use pulled pork, which is much better of a sandwich. So you start with your Go Ethereum implementation, right? This is like abstractly called L2Geth.go here, right? But the point is it's Go Ethereum. It's the main Ethereum client that everyone uses. What we do is we take that code base and we compile that to a very, 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 very simple VM, right? Remember that we have here, we want to minimize everything. And we use a reduced instruction set computer, MIPS, to make that a really, really, really small, it's like less than 600 lines for the main Solidity file. We compile Geth to that MIPS VM. Then we run the interactive dispute game on that, right? So this is the true bit thing, this is the Arbitrum thing, right? You basically narrow down on a single little VM step that you disagree with out of this large, broad VM execution, and you just run that one step. Okay, how we sounded? That making sense? Can I get some head nods? Yeah, okay, all right. That's an acceptable number of head nods. I like it. Okay. So what I want to talk about here today is basically the two hard problems that we had to solve in developing Cannon. And the two hard problems generally that come about when you're trying to build a rollup. And honestly, these are the two hard problems that there are other solutions to that if you get it wrong, it makes it not quite sit right, right? This is the place where you have to find the right abstractions. And it has taken a long time, but we've finally gotten there. So what are those two problems? The first problem is how to deal with inputs. Okay, so hopefully you guys are all familiar with rollups in the sense that we take data and we put it on L1 and we sort of notarize it and we leave it there and we use that during a dispute, right? Hopefully we're all familiar with that. But there's a lot of ways to go about doing that. You could submit that to a smart contract. You could submit it to something else if you're crazy, right? As long as it's on L1, you might not even send it to a contract. But somehow you need to take this call data, and during a dispute, during the fault proof, you need to verify that the transaction data that we're talking about that's being disputed is the transaction data that was posted originally. So that's the first hard problem. It's basically how do you verify the call data. The second hard part of this is persisting state. So what does that mean? Basically, that means, right, imagine that we've had a rollup and it's run for 1,000 blocks, right? And on block 1,001, we want to make a fault proof. There's something faulty about the proposal. We want to correct the system. This is what gives us all the advantages, is that for those first 1,000 blocks, we didn't have to do anything because the claim of the state was correct. We got these cheap transactions. We didn't have to do anything. But on the 1,001st, we have a problem. What you don't want to do is then go and say, well, here's how you prove the 1,001st block wrong. Well, first you start with the 0th block. Then you execute the first. Then you execute the second. Then the third. Then the fourth. Then the fifth. And all the way up to 1,001, right? You can't do that. What you want to do is start at block 1,000 and show that from block 1,000 to block 1,001, that is where the fault occurred. But to do that, we need to know what the state was at block 1,000. And it turns out that that is the other hard part of this. It's kind of statelessness in some sense, maybe in a bit different of a term than you might hear it in L1, but indeed it is the problem of persisting state. Okay, so these are the two hard problems of building these systems, right? If you just wanted to run a program that computes the first 1,000 primes, you wouldn't have either of these problems, right? Because you don't need to put an input, you don't need to put transactions through that program. You just run a program that computes it. And you also don't need to store state because it's a one and done, right? You start with an empty set of primes and you just keep enumerating all the primes and the program just runs. And so that makes it, that's basically what TrueBit was, and the problem was you can't have a database in TrueBit. So these are the two hard problems. Sound good? Making sense? Can I get nods? Okay, all right, we still got some nods, that's good. So I'm here to tell you guys today that there is one magical solution, one beautiful abstraction that we have fallen in love with that solves both of these problems. And that is called the pre-image oracle. Ooh, look at that. Oh, I've got some lag here. I wanted to go back and forth between SpongeBob and the pre-image oracle is like, ooh, ah, but we're too slow, so our clicker's not gonna let us do that. Okay, so it's called the pre-image oracle, and it's basically a new singular addition that you make to this MIPS VM. And the function is actually incredibly deceptively simple. The input to the function is a 32-byte hash, and the output of the function is the pre-image to that 32-byte hash, okay? So that sounds very simple, right? We have a very simple function signature here, but it's not so obvious that that is even a legitimate thing to do, right? If you are astute, you will tell me that a hash function is by definition pre-image resistant, right? So you can't just be given a hash and know the pre-image. That's the whole point of a hash. So what is the solution to this problem? Why does what I'm saying make any sense at all? The answer is quantum computing. Just kidding. Okay. I had to throw it in there, you know. No. Even, by the way, thank you. We'll take the applause. Oh, yeah. We can make hard problems funny. If nothing else, we got to do that. Okay. Hashes are resistant to quantum computing, by the way, as far as we know. Whew. Dodged a bullet there. Okay, so what's the real trick? What's the reason that we can get away with this? The reason is that in general, you can't find the preimage to a hash. But if you know the preimage to a hash, you best believe you can find it. You just store it. And indeed, it turns out that some preimages are just begging, just asking to have their preimage found. And I'm curious, if you're following along, you should start to think about, what is a preimage? What is a hash that is a preimage that everybody knows? What is an example of that? Can anyone think of anything? You get, did you all hear that? Okay, well, that was a major spoiler alert. I'm very pleased that you got that. The thing that I'll say before we go there, though, is that if you do know the preimage, then you can verify this step on chain, right? You basically do it in reverse. Even though a computer can't be given a hash and be told the preimage, if you give the computer the preimage and the hash, it can require that the hash of the preimage is equal to the output. And if that requirement is met, then it has all of the information to progress this VM, right? So in other words, I just got to figure out where to point this thing. I think it is fast. So in other words, if we know both preimage and hash here, it's a completely valid, understandable way to transition the state so long as we can meet this requirement. Very cool, very exciting. Not as funny as quantum computing, but it's very legit. Okay. So, this was supposed to be my slide, I guess, where I asked if someone could come up with it. And someone did. Someone yelled it out again. What is a preimage that everyone in the world should know? Yes, exactly. I asked the question in reverse, so what is the hash that everyone should know the preimage to? It's a block hash, right? The entire point of these distributed global consensus blockchain, buzzword, DAG, whatever you want to say, right, is that the block.hash has a header that is known, right? If you're working in Geth RPC land, this is get block by hash. If you're working in Solidity land, I actually think it's not block.hash, I think it's block hash. But anyway, you get the idea, right? If you have the block hash, you can know what comes from it, right? So here I just grabbed a photo of photo is an interesting word, a diagram of an Ethereum block header, right? And of course, you hash that to go up to the block.hash. You can think of the preimage oracle as a way to go in reverse, right? You input a block hash, and you output the whole header, right? And there's actually sort of more trees underneath here that you can see that you could also pull from sort of recursively. But this is very interesting. So in general, you can't find a preimage, but for an Ethereum block, you best believe you can always find it. So this is the solution to the first hard problem, that problem of input. What goes into the VM? It turns out that if we want to follow the Bedrock goals, which are to be super simple, super clean, super minimal code, the only input you really need is a block hash, because everything else is a subsequent state transition that you can pull out. Ooh, can I get an ooh, ah? Nice, okay, I like it, wow. Whew. That's a risk when you ask the audience to do that one on a question like this. This is sick, guys. I cannot describe to you how good this is. We spent so long at Optimism building this transaction chain. If you follow our code base, you've seen canonical transaction chain.sol all over the place. With Bedrock, we are getting rid of it. Yeah! Okay, I can't get you that far. I'll stick with the oohs and ahs. But this is a beautiful, very powerful thing. The idea that we go from all of this weird garbage, Solidity, hashing the call data, storing it on chain, we can replace all of that simply by putting in the block hash into the VM. Everything else falls out of that. Because the preimage is available, and by definition it's data availability, it's a rollup, you can get everything else. One other incredible property that we get out of this is that you don't even have to submit the data to a smart contract. So that is one of the craziest things you've ever seen. So one thing, oh man, can I do it? Oh, I'm gonna gamble. We're gonna do it. We're gonna go all the way back. So if you go to our reference implementation here in our specs repo, one thing you will not see is any smart contract that transactions are submitted to. In fact, the sequencer submits transactions where the to address is an EOA. There's no code there, no account, no bytecode. And it doesn't matter because it goes into the block header. And that's where the data is that you really care about. That's what makes it available. Very cool, very cool. Okay, so super bonus points if the person who thought of the first one can also think of the other thing that is a pre-image that's going to be very available to us all. Oh, snap! We got it. We're 2 for 2. I'm very impressed. Okay, you know what? You're right, and I reversed it now. This really should say state root. But the other thing that's always available is not just the block data of what all of the Geth nodes in the world are holding onto as the blocks. It's also the state data that they're holding onto as their EVM smart contract storage, right? So if we go back here, right? On the bottom left, there's a state root, right? And that state root itself is a hash of some children. And a whole point of the system is for it to store that data in the database, right, in the Geth state DB to make it available. So you best believe that if you have the Ethereum state, then you have the children of the Ethereum state root. And you have their children, and so on. And so basically you do this unzipping operation again, and you can basically traverse an entire state tribe like a database, as if it were stored in a database, but only using this pre-image oracle. Very, very cool. Very, very powerful. Wow. It's like hashing, but you do it in reverse. So that solves the second hard problem. And honestly, I wanted to just focus on these two topics because they are very counterintuitive. It's surprisingly simple to say, but when you really wrap your head around this, your mind opens up to the craziness of Ethereum. Suddenly, when I think of Ethereum now, after having worked on Canon, I imagine it basically as a single hash that is this special hash because everything behind it and underneath it is available. Because everything you can go backwards and get the preimage and get the preimage and get the preimage. And every part of Ethereum, as a matter of fact, is that preimage. Very, very crazy. Very, very crazy. Okay, so we can get there. With all of these things in mind, we can get there. The one true input to all of the rollup is just two things. Whoop. Not this clicker, that's for sure. It's one thing, we can put the entire rollup input as one hash, and that is the hash of the next block hash, right, where you pull the header, then you pull the call data, and the previous L2 block hash, from which you pull the state root, from which you can pull any state that you care about. Okay, so we went pretty quick, and I was hoping to do so because I was hoping to be able to take some questions, but that's it. This, guys, is some crazy stuff. I cannot tell you how much time we as a rollup community would have saved if we had understood this mental model years ago. Sometimes you just gotta try and learn and figure it out, but this is oh my God, this abstraction just makes me so happy and so excited, and so I hope I could share a little bit of that excitement with you today. Thank you. Oh, we're hiring. Woo! And we have 7 minutes for questions. I'm very proud of that.
Yeah,
I'm very proud of that.
It's absolutely amazing, and I must say, your energy gets me going, and I really hope that the questions are going to be like a tenth of the energy, right? Guys, some of you had the box, right?
It is.
It is there. Fantastic. So, by the raising of your hand, who has a question? Oh, there's a question. Yeah. No question then.
5 out of 10 throw.
Sorry, can we get the box working?
Uh-oh, they dropped it. Who would have thought?
Okay, I'll just come up with the mic.
If you shout it out, I can try to
No, because if you shout it out, it's not going to be on stream.
Oh, well, that's why I would repeat it. But.
So you mentioned that you can dump call data into any address, right? Because it's all wrapped into block hash, right? So I wonder, will this address start with 0x42069 or something like this?
Of course. It does. I think it does right now. I'm actually not positive of that. Maybe it's a 0 address. I don't know. But if you submit a PR to make it start with 420, we will absolutely merge that PR, Chris. Thank you. Yeah.
That's the spirit of Amsterdam, I guess. So, who has the next question? There you go.
I think we heard earlier today about the benefits of having multiple node implementations for decentralization and security as well. But then the MIPS VM that runs on chain is just one implementation, right? How do those two things play with each other?
That's a great question. Yeah, so I want to just go back to this slide because it just illustrates the importance of this, right? Everything that we're doing with Bedrock is about minimizing the diff and reducing it. So if you go to our reference L2 Geth implementation right now, which runs end-to-end test, deposit, transact, withdrawal, sequence, the whole thing, the diff for that entire code base from Geth to L2 Geth is right now sitting at like 400 lines. That'll probably go up a little bit, but it'll definitely stay under 1,000 lines. And one reason for that is because what we've realized over time is that nobody is good at writing code, and so the less code that you write, the better you are at writing code, right? So part of the reason is that, but the other reason to do that is going to make it really easy to port to other code bases. So I think it's going to be, I know it's going to be incredibly easy to look at a 400-line diff to Geth and port that over to Open Ethereum or Abesu or Aragon. And so that's part of the reason that we're doing that is because we do need multiple client implementations of these things. I had mentioned that earlier today. For those of you who didn't hear that, I would recommend that you guys check out Optimism's Path to Decentralization post. This is a really important piece for us where we go over kind of what we're talking about there, or talking about here. And the other thing that I'll say about it is, not only do you want multiple client implementations, but to your point, you want multiple VM implementations, right? So it only takes one to be able to get the system up and running. And so we're starting with one. But eventually, right, what you want to do is basically, I don't know what you would call this. It wouldn't be a sandwich. You could maybe like a Big Mac or something like this, because you would have multiple implementations and then multiple sandwich. I guess it's just multiple sandwiches, maybe like a foot long or something, because we've like extended this sandwich out and sliced it up, and there's different ingredients. Yeah, but it is very important. We started with the very simple, super basic MIPS VM. Maybe we can do a WASM. Maybe we should do a full-blown like RISC-V, right? But the idea is you can basically have a bunch of VMs under the hood, have a bunch of client implementations, and then you have, that times that number of different combos, and we think that that is the best way to get true security that we can actually remove upgrade keys on, because frankly, like Geth has already uncovered Golang compiler bugs, and so it is scary to do this, right? It is scary because there could be, it's really simple and elegant and clean, right? But you have this tail risk that you want to try to avoid. Yeah, so that's a great question, and we're definitely going to try to do that.
Okay, fantastic. We have time for some more, and I have the box, right?
Okay, can I have one more question? This time it's a serious one.
Quick, Chris.
What are the complexity limits of what you can stick into this interactive fraud proof? So basically, now you're executing like some arbitrary MIPS bytecode, right? And Arbitrum is doing something similar with WASM. Some things are easier to compile to MIPS, some others to WASM. You could compile WASM interpreter to MIPS and stuff any arbitrary WASM bytecode, right? And execute WASM on Canon, right? And what are the realistic limits of doing something like this?
So I think the correct interpretation of the question is, Chris just asked me, what is Turing completeness? Because in some ways, right, it's true that in any of these systems, right, you can implement any other one as long as they're Turing complete. And, something, Ethereum, Turing complete meme, all you need is the EVM, right? So the answer basically is that you can do any of these things. And I actually just talked to someone, I don't know if they're in the audience, but major shout out, who's taking Canon and writing a Tamagotchi emulator in it, which I'm so excited for, the first ever L2 Tamagotchi emulation. That is going to be so sick, so incredible. So the answer is you can do a lot. You can even do Tamagotchis, Chris. I hope that satisfies you. Realistically, right, it comes down to the number of VM steps that you're going to run, right? Eventually, you're going to run out of memory, and that's going to be like a hardware requirement for the fault prover. But in all the performance metrics so far with Canon, it's not a big issue, yeah. And I don't think Tamagotchis are harder to run than smart contracts. Maybe I'm wrong, but I think they're simple.
So I told this guy to compile it to WASM.
Oh, okay. Okay, we had one more question. Chris is hogging the box.
Okay, one more question is gonna be quick.
Oh, what a throw.
What happens with hard forks?
What's that?
During hard forks, do you know?
Oh, what happens with hard forks? Great. So you do want to have an upgrade path, basically to upgrade the executable that is running on the MIPS, right? So if we go back here, where are we? Whoops, right? So basically a hard fork, right, in L1 is changing the Geth, the Go Ethereum code base. And so if you want to incorporate those changes into your L2, you need to upgrade the executable that has been compiled. So you do need an ability to upgrade that executable. And that basically becomes the upgrade path for the L2 once you have this system running, is upgrading that executable after some block number or in some backwards compatible way. Yeah.
Okay, fantastic. Once again, thank you very much, Ben.
All right, thanks, y'all.